Hello everyone, we are in section 1.3 and in section 1.3 we would like to give a precise definition of a limit. Now back in section 1.1, this is how we define the definition of limit of a function. We mentioned the limit of a function if it exists. Not all functions do have limits, or I should say the limit doesn't always exist, but if it does exist, it's going to be that limiting value L, so that the function actually approaches, right, the limiting value L, as we approach x from the right and from the left side, a specific value which we call a in our discussions. So again, the limit is that value that the function approaches as x approaches a certain number. Now, something in this definition that we were kind of vague and we didn't really define precisely what we mean by it were these highlighted phrases that I have. We said that f of x can be made as close as to L. Or what do you mean by as close as to L? And we also mentioned we can achieve that by making x sufficiently close to a. Well, what do you mean by sufficiently close? How sufficient is sufficient? Okay, so that's what we want to address in this lecture. Now, before I give you a rigorous definition, a rather symbolic, I call it cryptic solution notation for the limit of a function, which I will do that at the very end of the lecture, because by then we have all the bases covered, and hopefully we all have good understanding of the precise definition before you actually see the precise definition. Because if I give you the precise definition right now, it's just going to look very cryptic, and it's like, okay, I see it, but I have no clue what this is telling me. Okay, so instead of doing that, rather than doing so, I want to actually go through an example with you. So let's begin. So in this example, let me actually make up my own example here. So this example, I'm going to call f of x to be a linear function. You already see a graph of this function. The function that I actually have in mind is going to be, it has a y-intercept of 2, and actually the slope of this line is 1/4 of x. Okay, or just 1/4, which is 0.25. So that's what I'm going to right here. So the equation of this line is 1/4 x plus 2. Very simple. Now I picked a linear function because everything's going to work out really nicely with this. I think it's a nice segue into more complicated examples that we're going to look at. After this, we actually look at a nonlinear function, and then I'll explain why this is easier, and that's what we want to start with. So let's say I want to find the limit of this function. The function, remember, is 1/4 x plus 2. It is a polynomial function, so we can easily find the limit. And let's say I want to approach x. I want to make it approach 4. Okay, so we can directly substitute into this polynomial function. Of course, simple linear functions are subsets of polynomial functions, right? So plug in a 4. So 4 times 1/4, that makes 1. 1 plus 2 is 3. Simple. That is a limit, right? I'm going to call that L. Now let me locate this actually on the graph. So on my graph, this is 4, right? Here's 4. And then the limit is 3. And this is what we're going to call L. And where the 2 crosses right in here. Now remember, the function need not be defined at that point. So, but it doesn't matter here. That's not our point. I just want to emphasize that the limit of a function and the value of the function don't have to be the same. Okay, if they are the same, then that's something nice which we will look at in the next section when we talk about continuous functions and we talk about continuity. So let's take a look at this. Now, so here's the limit, right? No big deal. Now let's go back and again look at the highlighted numbers. So what if I want to, let's say I want to be close to L now. I'm trying to clarify this part. Okay, we want to be as close to L as we want by making x sufficiently close to a. So those are the two things I want to clarify for you. So suppose this is a question. The question is, let's say I want to be within half a unit of the limit. Remember, the limit is 3, right? We know that. That's done deal. Now let's say I want to be within half a unit of the limit. Question, how close should I get to 4? The value on the x-axis. How close? And if you look at the graph, what I'm doing now is this. This is where 4 is, right? I want to know how close should I get to 4 in order to be within half a unit of L. Now, within half a unit of L, that means 0.5 less than 3 makes 2.5, and at 0.5 to 3, you get 3.5. Okay, so let me put the question. How close to 4 should x get in order to be within half a unit, 0.5 of the limit? Then these are all made up numbers. Okay, so the value I'm approaching for is arbitrary. And why did I pick within half a unit? I thought that's nice. You can say I want to be within quarter unit, within 1 unit. Usually with limits, you don't want to be within a kilometer of a limit, right? You want to be as close as possible to the limit. So for example, I want to be within 0.1. That's how close I want to be. Half a unit is too far away from the limit, but again, it's good for illustration purposes. So let's actually take a look at the graph now. Now, this would be L minus 0.5, right? Which is 3.5. That's where I'm at. And that's where this is. 2.5. And 3.5, that is L plus 0.5, which is equal to the 3.5. Correct? Because remember, the limit is 3. So plus minus 0.5 means give or take 0.5. Now, I'm going to just go ahead and travel along the x-axis here, right? Parallel to the x-axis. And this is where it's touching the graph. There. Now, I'm going to travel along the upper tolerance limit. And that puts me right about here. There you go, right about there, and that's at 6. I wish I had made my graph, my domain for when I capture the image. I should have gone to 6 or 7, but anyway, that seems to be 6. Now, if I but this will do. So if I project the number down now on the x-axis, looks like this number is 2. So this is x equals 2. And remember I'm approaching, where am I approaching? I'm approaching 4. Okay. So this is, sorry about this. Let me tidy up this number. Okay. So this is our A. So x equals 4. This is A. A is the value that the x is approaching. Okay. And then if I continue on down this way, I actually come to 6. This is x equals 6. Okay. Now, in order to answer the question, how close to 4 should x get in order to be within half of the limit? Well, it looks like I need to be, within 2 units of 4, don't I? Right? And we can actually now see where the number 2, this number 2 on the x-axis comes from. Let's say y is quarter x plus 2. I used the graph to find the 2 and the 6. I want to show you how to do it from the function. The value of the function is 2.5, and I want to find the x. So let's subtract 2 from both sides. That gives me 0.5. And then multiply both sides by 4. 4 times a half is 2, and there you go. I'm just trying to clarify and show you how you would do this without projecting from the graph, because later on we want to do this. And let's say, how did I find the 6 here, right? If I don't want to do it from the graph, again, you're going to say the upper limit is 3.5 equal to 1/4 of x plus 2. and then subtract 2 from both sides, I get 1.5 equals 1/4 of x, and then multiply both sides by 4. 4 times 1/2 is 6, and there you go. So you can actually find these numbers this way, the 2 and the 6. Okay, now this is all we really want to do in this section. I know I'm oversimplifying this, trust me, because the precise definition later on we use to prove the limit is a value. So right now the way I'm doing it is different than the way we'll do it later. Later the question is going to be like this. We're going to say prove the limit as x approaches 4 of this function is 3. Now that's a different question, but for now I'm just trying to get us acclimated, get us comfortable with the notion of the limit plus or minus a number, and then x plus minus a number. So in fact, let's do that. So in terms of a, now this value is going to be a plus 2, right, the 6, and the value of 2 is going to be what, a minus 2, isn't it? Okay. So again, in order to be within half a unit of 3, I need to be within 2 units of x. What if I want to be within 1/4 of the limit? So I'm going to go a quarter down and stretch this. There you go. That's where it hits the graph. Within a quarter puts me up here, and then stretch this one. There you go, roughly. So this is how, and this is, remember, this is 4. And this is how far you want to be from 4 in order to meet the 1/4 tolerance for the limit. So this would be like 3 1/4, and then on the lower end it's going to be 2.75. I'm doing plus minus 1/4. Okay, so there you have it. And let me now erase this part and just keep this tidy. Alright, hopefully you follow this example. Let's take a look at another example. Actually, before we look at this next example, let me emphasize one thing here before we leave this problem. Notice that the distance of 2 units from A, again this is A, and we went to the right 2 units, left 2 units. This is a symmetric interval, right? Symmetric in the sense that you are equal distance away from 4. So you go right 2, left 2. Again, this, we would expect this to happen. Is it always within the same amount from A as we are within, let's say, plus minus this amount for the limit? For linear functions, yes. So if I made up another linear function and we want to find how close we should get to A, the answer is going to be, again, a symmetric interval. So the answer is going to be 2. And in fact, I didn't finish the answer to the question. How close to 4 should x get in order to be within half the limit? The answer is 2. You got to be within 2 units in order to meet that, requirement. Now we can look at actually a different example. Okay, now let's take a look at this next example. So for this next example, I'm going to choose, here's our next example. Let me change my pen to a different color. Okay. Okay, let me make up this function. How about this? Let's say we go find the limit of x equals, x approaches 5 of a square root of x minus 1. Now this limit as x approaches 5 minus 1, 4 square root of 4 is 2. There you go. So again, for this one, let's say I'm gonna want to be within 1 unit of the limit for this one. Okay, so I'm just gonna say find how close we should get, or we should be, to x equals 5 in order to be within 1 unit of L equals 2. Remember, the limit is 2 here. Okay. And then later, after this one, I begin to use symbolic notation rather than just verbiage. Okay, so let's actually graph this function now. I'm just going to, well, let me use Desmos, okay, because I want this to be as accurate as possible. So let me actually put my graph out of Desmos. Okay, so here is a graph. I grabbed it from Desmos, but again, this isn't difficult to graph. Let me do this real quick, show you how I do it by hand, and then I'll look at the clean graph. So if I was to do this by hand, I know the square root of x looks like this, right? That's the square root of x. Now, x minus 1 in the radicand causes a horizontal shift to the 1 because at 1 you get 0, so this is where old 0 used to be. The new 0 is here, and then you just redraw it. And that's the graph of a square root of x minus 1, which is precisely what this is. And here's point, that's the one that's on my graph. So again, it's not difficult to graph. I do it because I want it to be precise because this is a sensitive topic. Okay. Now let's take a look at this. So keep in mind again, we want to be within 1 unit of the limit from 2 as x approaches 5. So first of all, here's a equals 5, right? On the x-axis. This is your x-axis, and of course this is your y. Now, within 1 unit of 2, well, the limit is 2. So again, right in here, this is where L equals 2 is. Within a unit means I need to go up 1 unit, so this is going to be L plus 1, and go down a unit, L minus 1, which of course puts you again at 1, and here it puts you at 3. Okay, so in order to be within 1 unit of the limit, now let's see how far we need to go on the x-axis. So first of all, there you go, this is where it hits the graph, and on the high side, there you go, this is where it's hitting the graph. Notice this is a nonlinear function, and that's what I was referring to earlier. For linear functions, you would expect a symmetric interval about a, but this time you don't have a symmetric interval about a. We will not. Okay, so let's actually, I'm going to highlight how far we have to be away from A now in order to meet that 1 unit tolerance for the limit. So it looks like if I highlight it, it's going to be from here all the way to the right up there, right? Again, on the low side, and on the high side, it's going to be from here all the way, it looks like, to 10. Okay, so that's what it seems to be. The value here, we need to find that number, and we do need to find this number. I know it's 10 and I know this is 2, but let's find it algebraically. So remember, if you know the value of the function, you want to find x, you plug in for the function. In this case, I want to know what the lower number is, right? So I'm just going to put 1 in the function. My function is the square root of x minus 1. I want it to be 1. And then we need to solve for x. Squaring both sides, give me 1 squared equals x minus 1, so x must be 2, right? Add 1 to both sides, and this gives you 2. Okay, so on the low side, this number, this is going to be a 2. And what about the number 10? Well, we want to set the function value equal to 3. We want to know for what x, y would be 3. Square both sides, and we get x minus 1, and x is 10. So there we have it. This is x equals 10, and this is x equals 2. So we got it from the graph, but it's consistent with our algebraic steps. All right, so there you go. It's really that simple. How close should we get to 5? Well, in case of a non-symmetric interval, in this case, which is what we have, in order to meet the lower tolerance for the limit, that's L minus 1 equal 1, I need to be only to within what? From 2 to 5, that's 3 units. And in order to reach the upper tolerance, I need to be within, from 5 to 10, the distance is 5 units. Now, we don't have two separate answers for the question. We're going to have just one number. Okay, so we're going to go with the smaller number, and here is y. If I go with 5, the higher number, so that means I'm going to extend the lower number, right? If I need it to be 5, that means this 3, which is on the low end of on the x-axis, I'm going to have to go 2 more in order to match the 5 that's on the other side. So that puts me at x equals 0, doesn't it? Now when x is 0, notice for one thing the function isn't defined in there, right? So, and that's going to put me clearly it's going to put me outside of my lower tolerance, which is L minus 1. Now if I go with the smaller number, let me erase these. Okay, now if I go with a smaller number, that is 3, look what happens to the upper tolerance for the limit. Well, at 3 we know we have met the L minus 1 tolerance, right? Because that's exactly where we are, within 3 units of 5 on the left. L minus 1 is where we're at. Now let me go just 3 units higher. 3 units higher above 5, that puts me at 8, right? There you go, 3 units above 5, and this is where 8 is. Now if I extend this to where it hits the curve, and then right here I'm going to project to the to the y-axis. Okay, in other words, take a look at the y-axis here. Look that I'm just barely above 2.5, so I'm actually doing better than +1. Remember, the requirement here says I want to be within 1 unit of the limit. So as long as I'm up to 3, that would be 2 plus 1, up to 3 for the limit, I'm okay. I mean 1 unit, I shouldn't say at 3 for the limit. As long as I'm 1 unit above the limit, that puts me at 3. As long as I'm above 1 unit from the limit, I'm okay. And actually I'm doing better than 1 unit away. This distance right here, this is less than 1 unit. So that's why we choose the smaller of the two for nonlinear functions, because we know we're doing better on one end. Okay, so hopefully this makes sense. Okay, so the answer to the question, find how close we should be to x equal 5 in order to be within half a unit of L. The answer is going to be, let me write it using a different color possibly. The answer is within 3 units. That's how far we should be, within 3 units of that. Okay, and that completes this example. Okay, so what we just did, let's now write it a bit more symbolic here. Okay, this is a nonlinear function just like the one we had. It looks like a parabola, but that doesn't matter. It's just a nonlinear function. So now if you look at actually here on the y-axis, the limit of the function, that's L as we approach A, right? So this function does have a limit, and the limit is L. Now in general, what we want to do, instead of putting numbers like I want to be within a half or within a 1 or so on, let me change that. This should actually be a plus in there. Okay, so symbolically in a general form we use epsilon. That's what the symbol here is. It's Greek letter epsilon. And the one that's on the horizontal axis, how close should we get to A? The distance that you're away from A, the how close part is a delta. So that is what this is. So those are our 2 Greek letters that we use in here. Okay, so in order to be within epsilon of L, so I'm looking at L plus or minus epsilon, that's what this interval is, you need to be within delta of A. So this interval is going to be a let me erase. Okay, it's going to be a plus minus delta. Okay, and this is precisely what we just did. If you look at again the example we did up here we had L plus minus 1, and this A was 5, and then we're going 5 plus minus 3. Right, that's what A is. In general, we want to be within delta of A in order to be within epsilon of L. Now let's take a look at another example where we're going to have an epsilon actually to work with, and then we're going to find our delta. Okay, let's take a look at this example. This is actually an exercise in your book. It's problem number 10 in your textbook. And here we are given the epsilon to be 0.5. So we want to know how close to 2 x approaches 2. How close to 2 we have to be. And this is what the A value is. In order to be within 0.05 of the limit. The limit is actually 1/2. Okay, so if I draw this, and this time I'm going to draw this just not with Desmos but myself. So this is the portion of graph of 1 over x. The other part of it is here, right? So that's that part of it. Maybe my vertical axis is not quite vertical. There you go. And anyway, we don't need this other part of it, but if you want, this is the graph of 1 over x. Now, x approaches 2, so let's say this is where 2 is. Okay, and at 2, the limiting value is 1/2. Okay, and my x and y axes are not drawn to, or let's say they don't have to have the same scale. Therefore, it's okay that the distance from 0 to 2 and 0 to 1/2, they don't look proportionate, but that's okay. Now, the epsilon tolerance is what they call this. The epsilon tolerance is this. L plus minus epsilon, we call that epsilon tolerance. In your book, they may show it as L minus epsilon to L plus epsilon as an interval. And then your delta tolerance, let me write that one for you also. Delta tolerance, that's going to be A plus or minus, let me actually go higher. It's going to be A plus or minus delta. In interval notation, that would be A minus delta, comma, A plus delta. Okay, so those are the tolerances. Now, to be within 0.05 of the limit, so I'm going to go 0.05 above. Now I'm going to exaggerate 0.05 just so you can see it better on your graph. Otherwise, they're not really that high. This is notice, by the way, how small epsilon is. And epsilon, by the way, the epsilon tolerance will always be symmetric in that we always go plus minus epsilon. But our delta, again, we have to adjust it for non-symmetric intervals. Okay, so the higher number, the number up here, this is going to be L plus epsilon, and the lower number is L plus epsilon, right? That's my epsilon. So it looks like I have to go this far. This would be 2 plus, let's say for now I'm going to go delta 2, the higher one, and this one is going to be 2 minus delta 1. The reason I'm not using delta on both, because I know I have a non-linear interval, and you can see even from my graph, let me enlarge it. Ooh, beautiful. You can see from my graph, see that distance right here and that distance, they're not the same distances, are they? So that's what this is. This is delta 1 and this is delta 2. That's why I'm using a subscript to differentiate between the two of them. Okay, and it's gonna really look small, but you saw the enlarged version. Okay, now let's do this. So in order to reach the lower limit, that's 2 minus delta 1, the value of function at this point, that's 1/2 plus epsilon. So L plus epsilon, actually let me not use red color, let me use a better color. I'm just going to go with black color here. Okay, so the L plus epsilon here is going to be 1/2, which is 0.5 plus 0.05, that makes it 0.55, and then L minus epsilon is going to be 0.5 minus 0.05, or 0.45. Okay, that's going to be my epsilon tolerance. It's going to go from 0.45 on the lower to 0.55 on the upper limit. Now, we want to find the x value corresponding to 0.55. So I'm just going to go y equal 1 over x. I want to know for what x y is 0.55. Okay, and in order to find this, now multiply both sides by, well, you can do 1.55 equal x. There you go. And x is going to be 1 over 0.55 is going to be 1.818. Okay, now for, that's the lower number, this is 1.818. Now the higher number for x, again I'm going to the equation y equals 1 over x, and from this I'm going to get 1 over 0.45 equal x, which makes x equals to 2.22. Okay, and that's the higher x. This is going to be 2.22 on the x-axis. All right, and now notice again we don't have a symmetric interval. So let me just do what's going on around 2. This is a equals 2. The higher number, I'm magnifying the distance away from 2. This is 2.22, and the lower number is 1.818. Okay, now again, because we have a non-symmetric interval, we have to choose the smaller of the two intervals. Okay, so the smaller of the two interval is going to be this one, right? That's going to be our delta, and that's what indeed we're going to choose for our delta there. So we're going to say our delta is the difference between 2 and 1.812 minus 1.818, and that number is going to be 0.182. There you go. Delta is 0.182. So if we choose delta to be 0.182, we're going to be within half a unit of the limit. Now on the higher end, we know we're going to be actually less than half a unit, right? Because remember, this upper distance, this was 0.22, and we are at 0.18. We are right about here. So when you go project onto the curve, instead of, let's say, hitting here and projecting, you're going to hit at a higher point and project. So that means you're going to be even closer to a half than 0.05. Okay, and we can see exactly how far, but that doesn't matter. Okay, so there you go. You have this example. This is exercise number 10 that we just looked at. Hopefully you can follow this. No, we haven't proved the limits. So in order to, and what I mean we haven't proved the limit is that we haven't proved the limit of the function is this. Now before we do that, next we're going to actually look at a formal definition of the limit of a function using now epsilon and delta in order to justify how close to L we should get, and to clarify the phrase sufficiently close to A. Okay, so I'm going to write that. Actually, before we take a look at the formal precise definition, let me let me do this. I'm going to go to Desmos and actually illustrate what we did with this exercise just now. Exercise 10. We're done with it, but I want to show this on Desmos, okay? And we can look at an animation where I can, again, I want to make sure you really get this epsilon delta thing. So when we go to the proof, then it will make more sense. Now, one thing, by the way, the value of delta is not unique, just to mention that. We found delta to be 0.182. 0.182 will meet this requirement of epsilon equal 0.05, no problem. But what if we use 0.1 for delta instead of 0.18? In other words, what if I get closer to 2? Well, as I get closer to 2, let me show you that just on this real quick. As I get closer to 2, and that's good enough. Okay, let's say this is where 2 is. And this is the limit of 1/2, right? When I get closer to 2, I'm going to be very close to 1/2, aren't I? Look at that. So I may not even, anything really nearby, near 2 is going to be very close to 1/2. So I'm doing better on that epsilon of 0.05, right? Let's say this is my 1/2 plus minus 0.05 would be, and this is 1/2 plus 0.05. That's my limit. Well, once I get closer, and this is what we found. This we found to be 2.22, and this we found to be 1.818. So this is what I'm saying. Notice I'm actually much closer to 2 than being 0.182 away from it. So once we determine the value of delta, anything smaller than that value of delta will also work. Okay, so we just found a single delta, but anything less than that will work. Okay, so let me now go to Desmos. Now I'm in Desmos, and I actually have our function. Okay, so the square 1 over x, the function is actually there. Now for this one, and you can kind of see on the screen, now my marker, I realize if I touch my digital pen on my touch screen, it will not work like it does in OneNote. I don't know why, but it doesn't. Let me make sure. Let me try this other marker. Maybe this one would work. Yeah, this should work. Let's see. Yes, it does. Okay, fantastic. But the eraser doesn't work on it. And let me pause. Okay, I think this is going to work out. I hope so. So let's see. So here's my function. Yeah, it's working. That's f of x. Okay. This part, this is your epsilon tolerance. Okay, we will write that in a few minutes, but that's another way to write your epsilon tolerance. And this one is your delta tolerance. Okay. A is the value we are approaching to. This would be epsilon, and this would be delta. So that's how we wrote them. Okay, it's just in Desmos they use English letters. Now, so once we have those, let's take a look at now what's going on with this graph. So this would be A is equal to 2. That's where I'm at. Now notice the limit is 1/2. That's the value here. This is 1/2. Okay, let me, I can, enlarge it. Hold on. Okay, I think I got it. It's really hard to adjust this because this is animated and it just keeps moving on me. Anyhow, so you're gonna see the function here, f of x 1 over x. The second function is our epsilon tolerance. The third one is our delta tolerance. A is the number we are approaching. So that's 2 for our example, and you can see on the graph that that's actually 2. Now I can use my pen. There we go. This is the value of A right in here. This is A equals 2. Okay. The epsilon tolerance, there you go. Our epsilon is 0.5. Now, D here stands for delta. Okay, remember, that's epsilon, that's delta. And the value of the limit, of course, is 0.5. Now, in order to be within 0.05 of the limit, and the limit is right in here. This is 0.5, which is our L. Now within 0.05, that's what these upper and lower marks are. Okay, so this one is 0.55, 0.05 higher, and this one is at 0.45, 0.05 lower. Now notice delta, that would be along the horizontal axis. Okay, right now I am this far and this far, and in Desmos it maintains a symmetric interval. Okay, because of what's being mentioned up here, because of that statement. Okay, now I'm gonna get closer to 2. Okay, so that what I'm gonna do in a moment is this. My delta right now stands at 0.85. I'm too far away from 2, and that's why if you look at these numbers, see, I am outside. I need to get closer to those epsilon tolerances, right, to be within 0.05 of the limit. So in order to accomplish that, I'm gonna have to move closer to 2. So what I'm gonna do is I'm gonna actually move D. I'm over here, folks. Okay, I'm gonna move D closer to 0.2. Remember, our answer is almost 0.2. So I'm gonna move left, and look what happens to the band that we have. Okay, to that band. And let me get rid of all these extraneous marks, and then I'm gonna move this now. Okay, you ready? And I'm moving to the left now. Look at the band, how it's shrinking. You see that? I'm still outside of my epsilon tolerance, aren't I? True. You see these circles that are up here again, this one and this one. Okay, I'm still outside of the tolerance. I want to move until those dots appear nearly here and here. Okay, so that's our objective. So that means I'm gonna reduce my D, and look at that, it's coming in. I'm getting, so this is what I mean by sufficiently close to A. I'm too far away from 2. I need to get closer to 2, and I am, and I'm almost there. And there you go, just about. Look at D at this point, 0.2, and look at these circles are almost touching. Now, of course, if I enlarge this, you will see, and let me do that, hopefully things don't go crazy on me, but this is pretty much what it needs to be. So I'm within 0.05 again, right in here. I'm within 0.05 of a half, and right down here, A is 2. I'm within about 0.2 of 2. So this is what we mean, and this is by, again, closeness and how close we need to be in order to meet the epsilon tolerance. Now let me enlarge this. Oops, actually, there, I'm trying to enlarge it as much as I can without making it go nuts. Okay, and then let me shrink my, well, D is 0.2, and look at that 0.2. You kind of see that okay, this one at 0.2, one of them, see, that's because of the non-linear nature of this curve. I'm already inside the epsilon tolerance here, but at 0.2 I'm not there. Remember, that number should have been 0.18. In other words, this is A equals 2. I should be right about here-ish. And that distance, this from here to here, that is what the 0.182 we found it to be. Okay, and anyway, so that's what's going on with this thing. Okay, so hopefully you have a good grasp of this epsilon delta. I probably beat it to death too much, but the reason I do, because students really have trouble with epsilon delta proofs, and now hopefully you have a good foundation for this, and we're going to truly next gonna look at the limit of a function at a number, and we'll see how your author will explain that. Okay, so this is where we are, and this is now what we call the precise definition of a limit of a function at a number. So I'm just going to read over this with you. Okay, so here we have a function. Let f be defined on an open interval containing a. Remember, a is the value that we are approaching, what x is approaching, and these are two-sided limits, by the way. A modification of this works for one-sided limits of this definition, by the way. So we do have an open interval containing a, and the function need not be defined at a. Then the limit of f of x as x approaches a is that number L, written as the limit notation, this, and here is the part that's kind of what we've been doing, right? This is the part that we have done through examples. Now it's kind of cryptic. If for every number epsilon, by the way, has to be positive, okay? The epsilon has to be positive. Then we can find a number delta and epsilon are both positive, in fact, okay? Such that the absolute value of x minus a lies between 0 and delta. In other words, what we're saying is that the difference between x and the limiting, the value that we approach is going to be less than delta. So this part of it defines how close, this is what we mean by how close we need to be x, right? Close to a we need to be, not x. And this one is how close we want to be to the limit, okay? So that's how we justify those, and that's how in notation that is written. Okay, now I'm actually going to write this even in more cryptic notation. Okay, now in order to do this, let me define a couple of things here. We have these quantifiers, okay? Okay, so we're going to use what we call quantifiers. Now, here are a couple of quantifiers that I'm going to use. Okay. So we're going to use what we call quantifiers again. So first of all, we have this universal quantifier. The universal quantifier looks like this. Let me write it as universal. And this is quantifier. Okay, now this quantifier means for every, for all, or for every. So the part up here that says for every, we're going to use the universal quantifier. The other quantifier is the existence quantifier. It's like backwards E. This is called the existential quantifier. And here is quantifier. What does that mean again? That means there exists. Okay. So rewriting this using this notation, here's how I'm going to write the epsilon delta definition. And in fact, that's what this is. This is commonly called the epsilon delta definition of limits. Okay, so here we go. I can say that for every, okay, if for every epsilon positive, number epsilon positive, there exists a delta that is also positive, and such that, here's another quantifier, there you go, this one. Remember the set membership notation, that one? Well, if you again write it backwards, that means such that. Okay, so such that. And then I'm going to write down what the author has, that for x minus a, absolute value x minus a less than delta, for that, this means basically for any number that gets you as close to a as possible, right? So that it's delta or lower. Remember, anything, once you find delta, anything less than that works. That's what this says. The fact that delta is positive, that's why we have it greater than 0 here. Okay, then this implies that the difference between the function and the limit is going to be less than epsilon, and we need absolute value because we chose epsilon to be positive. This guarantees that the difference will be positive. Okay, and there you go. Now let's see, just again a general note. I mentioned about this being known as epsilon delta definition. So as far as how we're gonna now, okay, once we have this definition, what's gonna happen next? What's gonna happen is that they're gonna ask us to prove the limits or whatever they are using this definition, epsilon delta definition. So in order to prove a limit is whatever they say it is, it's a two-step process. First, we need to find delta. Okay, so we need to discover what delta is. So let me actually now write this for you. Okay, I need to let me get my pen. I'm having trouble with my pen here. Sorry, folks. I'll get it to work. There you go. All right, I'm back on. Now, two-step process to prove a limit using epsilon delta definition. Okay, what do we need to do? We need two things. First, we need to discover or find a value for delta. Okay, that's our first step. Okay, and then second step, we need to prove that the absolute value of f of x minus L less than epsilon holds. Actually, it holds for that discovery, for that delta that we just found. Okay, and again, I already mentioned delta isn't unique, so once you find delta, any smaller positive number will also fulfill the requirement or epsilon tolerance. Okay, and let's take a look at, how about if we take a look at an example where we want to prove that the limit of something exists and it's the value that they say it is. Okay, let's take a look at an example. Okay, in this example, we want to use the epsilon delta definition to prove the limit. So let me do that. Use epsilon delta definition to prove. First time you're formally proving something. To prove that the limit as x approaches 2 of 3x minus 5 is equal to 1. Okay, so that's what we want to prove. So what do we need to do? Well, we need to show that for any positive number epsilon, we can find a positive number delta, such that, and this is what we need to prove. We need to prove that the difference of 3x minus 5 minus the limit of 1, remember this was f of x and this is L, it's going to be less than epsilon if we can find a delta such that x minus 2, that means the difference between a and the value of x is going to be less than delta. This again, this part, the last part, tells us how close we need to get to a. The first part, how close we need to be with L. Okay, now there are two things we need to do here. First, we must again discover a value for delta, okay, for which the statement holds. The statement that we have holds. Okay, and then the second step, we must prove that this statement holds for that delta. Okay, So for the discovery part of our work, let's begin this way. Okay, we're about to discover our delta. So here's how we're going to go about it. I'm going to write 3x minus 6. Remember, that's negative 5 minus 1 up here, right? Earlier, directly above that. That's where the 6 comes from. 3x minus 6 is less than epsilon if 0 less than absolute value of x minus 2 is less than delta. Now, next, we're going to, let's rewrite the statement, okay, in the form that will help us discover the appropriate delta. And here's what I mean. I'm going to factor a 3 from the left absolute value and then divide both sides by 3 epsilon third. Okay, now on the right side we have 0 less than absolute value x minus 2 less than delta, right? Okay, well, if you look at, forget this part of it, this part. Now, if you look at these two statements, the left side of both inequalities are the same, so that means the right sides, we could equate them together, right? So this last statement holds, what I have here holds if delta is going to be epsilon over 3. So, for this function, the linear function, if you want to be within whatever your choice of epsilon is, how close do I need to get to 2? You give me your epsilon, a third of that. That's how close I need to be in order to meet your epsilon tolerance limit. And I'll show you that in just a moment with an example that this will work. Okay. Now, so this completes what we call the discovery portion of our work. We discovered delta. Now, in order to prove that the statement up here holds, to prove this, right, in order to prove that statement holds, what are we going to do here? Okay, so I just want to give you a moment to think, how am I going to do this? So in order to prove this, well, this statement number 2 that I have, this one, not number 2, I was thinking at this one. Okay, this statement that I have is equivalent to the statement that's down here, right? Because again, only difference is this part, and remember the part in the box came from that. So these two statements, 1 and 2, up here and down here, these two statements are the same, okay, are equivalent. And this last statement, the one that I worked with, this last statement actually holds and is true when delta is epsilon over 3, right? So that the original statement we wanted to prove also holds with delta equal epsilon over 3, and therefore this proves that the limit is 1. So, to kind of bring it together now, in order to prove the limit exists, all you gotta do is to find a delta, okay? To find the delta. Once you find the delta, because delta has come from this statement, which that statement has come in turn from the original statement. So if delta works in this statement directly above it, then it has to work in this one, right? So that's the part 2 of the proof. There's nothing else to do. Okay, now let me show you that this delta equal epsilon over 3 will meet the requirement. So I'm going to make up an epsilon value here. Okay, so let's do that. In this next example, again, it's a continuation of this one. I just want to show you how this delta and epsilon over 3, what's the role that they're playing here. So let's say I'm going to make up an epsilon here. I want to be within, let's make epsilon 0.3. So delta works out nicely. Okay. If I want to be within 0.3 of the limit, which is 1, limit is 1. Of that, we just found that delta must be epsilon over 3, and that is 0.3 divided by 3. Okay, I need to be within 0.1. Let's see if we can verify this. Okay, So without going to decimals now, I'm just going to do this so it will go a little quicker. The function is what? 3x minus 5. So 3x minus 5 is going to look something like that. Okay. And let's say this is where 2 is. Okay. The x-intercepts is at 5/3, right? 3x minus 5 equals 0. Yeah, 5/3. Okay. Now, here's what I'm going to do. There. The limit, we just found it to be 1. Okay, the limit is 1 by direct substitution. I want to be within 0.3. So, there you go. This is 1.3 and 1 minus 0.3 is 0.7. True? So, in other words, L plus epsilon is 1 plus 0.3, which is 1.3. I don't need a decimal here. And L minus epsilon is going to be 1 minus 0.3 or 0.7. Okay, now, how close do I need to get to 2? Okay, to see how close to 2, let me switch my pen. How close to 2? Let me extend this and drop it down. There you go. We need to find this number. What is this number here? That's the function value 0.7. Set it equal to 3x minus 5. So add 5 to both sides. And when we add 5 to both sides, we're going to get 5.7 equal 3x. And divide both sides by 3. So that's 5.7 divided by 3. That's like, let's see, 57 by 3, 19. So that's 1.9-ish. There you go. So this value is 1.9. That's what we just found. Notice the difference between 1.9 and 2 is 0.1. So this distance is 0.1 so far. Now, if I go to here to 1.3, drop down and try to find what this number is. This number. Okay, so y is 1.3 equal to 3x minus 5. Add 5 to both sides. I get 6.3 equal 3x. And now x is, 2.1. Okay, so x is 2.1. And that's what that is. Notice the symmetry of the two. This is 0.1 and that distance is also 0.1. So that is what our delta is. Delta is 0.1. And that's exactly what we were saying here. You give me your epsilon and I'll give you the delta. So here I chose an epsilon of 0.3, and for that choice delta must be 0.1. If you want to be within 1 point of the limit, within 1 unit of L, you need to be within 1/3 of the distance to 2 on the x-axis. Okay, so this is how we prove the limit. So let's take a look at now. Let me get another example. Let's go to the book. Okay, so let's begin with exercise number 12. And in this section, by the way, when it comes to proving the limits, this is in line with pretty much what I want you to know. As far as going to future, by the way, future chapters, we are not going to use this way the epsilon delta in finding the limits. As you can see, it can be cumbersome, it can be problematic. So we stick with our limit laws in finding limits, maybe sandwich theorem, but this is what the precise definition is. You will see this. You will see this kind of a definition, the epsilon delta definition of limits, in your 3rd semester calculus also. So it is something you will encounter, you will come across later on. I don't recall seeing it in the 2nd semester calculus, but definitely in the 3rd semester calculus you will be working with epsilon delta. But for purpose of Calc 1, as long as we can do something like this is perfectly fine. What you're looking at, numbers 11 to 22, and of course within number 10 where the problem gave us an epsilon and we found a numerical value for delta. For these exercises, the one that's in front of you. For these, you will not be able to find a number for delta. We're going to find something in terms of epsilon, okay? So let's begin with exercise number 12 in this one. Okay, in number 12, we want to show that the limit as x approaches to -2 of pi is pi. Now remember, this is a constant, right? So we're going to, this is number 12. We're going to begin with, let me switch my pen. We're going to begin with number 12. In the limit as x approaches -2 of pi, we want to prove that it is pi. Okay, so first let's start with our epsilon tolerance, f of x minus L, and f of x is pi, the limit is pi, and the difference is 0, isn't it? Now, as long as we choose epsilon, remember epsilon is a positive number, because that difference is 0, sorry, because that difference is 0, therefore any positive epsilon will work in here, right? Epsilon is going to be positive, and for all x, right, this is true. And because of this, any delta would work, because the expression is independent right in here. See, 0, it's independent of x. There is no x to work with here. So for any delta, you satisfy the definition. So in other words, if I say I want to be within 0.5 of pi, well, remember this is a constant function. Here is y equals pi, right? That's 3.14. This is pi, and here's x. No matter where you are in here, you're always, see, you're always on the line. So it doesn't matter how close you get to any delta, you always be pi, because there is no epsilon tolerance here, because it's a constant function. So any positive value of delta would work. Okay, in fact, that is true for number 15. It's the same thing, right? In number 15, any positive delta would work. So delta in this case is chosen arbitrarily. Okay, let's take a look at another example. Let's say we want to take a look at which one would be good. Something like I don't know, maybe the linear functions we have seen. Let me take a look at this. Okay, let's take a look at number 18 actually. Maybe you might want to try number 17, but we'll try number 18 together. Okay, in number 18, we want to prove that the limit as x approaches 2 of x squared minus 2 is equal to 2. And by the way, folks, this is one of the most problematic sections in this course. The epsilon delta definition and proving limits using epsilon delta is not favored by students at all. So if you find this kind of you're a little uncomfortable with this, don't worry, it's not just you, it's a lot of students. I remember when I was a student, I always had trouble with this myself. It's just the concept is kind of bizarre. Anyway, so we want to prove this. How are we going to prove it? Remember, we need to discover delta and then prove that it works for the absolute value of f of x minus L less than epsilon, which we're going to wave our hand over that because the way we arrive at delta. So in other words, it amounts to a discovery only, really, okay, for our purposes. So here's how we're going to start this. We're going to begin with absolute value f of x minus L less than epsilon. Okay, so remember our f of x is x squared minus 2, and we're going to minus L. L is 2, the limit is 2 less than epsilon, and I can write this as absolute value of x squared minus 4 less than epsilon, which we can write the expression inside absolute value. We recognize difference of two squares, so we can write it as x plus 2 times x minus 2 less than epsilon, and then we can break it into two absolute values times x minus 2 less than epsilon. And we are using a number of properties, algebraic properties, when we use epsilon delta in this particular example. Let me put this part on hold now and actually focus on absolute value of x minus a less than delta. A is 2 in this case, right? 2, that's what a is. So that's going to be x minus 2, absolute value of that, less than delta. And this we can write it again using our algebraic knowledge as x minus 2 less than delta. So a couple of algebraic manipulation here. First of all, this is the property that I'm looking at. Absolute value of x less than k means x is between negative k and k. So this is again from algebra. Okay. The other thing that I used here with the epsilon inequality is absolute value of x times y is equal to absolute value of x times absolute value of y. So those are just from algebra. Okay. Now I'm going to add 2 to both sides of this inequality. That makes it 2 plus delta here and 2 minus delta. Okay. And then now let's see what our strategy should be at this point. Okay. So since we have product of two absolute values on the left side, what we wish to do at this point is we would like to actually bound the factor absolute value of x plus 2. Okay, we need to bound this, and the reason is this. You see this x minus 2, this one, absolute value of x minus 2, looks like this expression, doesn't it? And that's kind of already bounded, isn't it? That's less than delta. So the only thing I don't know about is absolute value of x plus 2. So I need to bound absolute value of x plus 2. Bounding mean, when we bound it, what do we mean by bounding it? That means I need to see how high can this thing get, how large can this thing get, this factor get. Okay, so what happens usually at this point? We need to choose what we call a convenient, quote unquote, a convenient value for delta. And usually in the textbooks they use 1, but anything you want, that would work fine. Okay, so it's pretty much an arbitrary value. So you can let delta be a half, you can let delta to be a quarter. Of course, the smaller the better, right? It means we're getting closer to actual value of 2, the value that x is approaching to. But in the textbooks, again, usually all calc textbooks usually get delta to be 1. So I'm going to do the same thing. And again, this is merely for convenience. Okay. So let me write this now. For instance, if delta is going to be less than or equal 1. Okay. Now, let's take a look at our absolute value of x minus 2 less than delta. And over here now. Okay. So we're going to let delta be 1. So I'm going to rewrite this again itself in the form negative 1 less than x minus 2 less than 1. That's just to write the expression without the absolute value. Then adding 2 to both sides gives me x between 1 and 3. Correct? Now, at this point, what I need to do is I need to make what in this inequality, I need to create that factor of x plus 2 that appears in my epsilon expression. So because it is x plus 2, I'm going to add 2 to all parts. So this is, I grant you this for sure, this is a creative step. Okay, and of course practice helps. True. 1 plus 2. So that means x plus 2 is going to lie between 3 and 5, right? So this is what we mean by bounding the factor x plus 2. We just showed that for a given value of delta 1, x plus 2 it's bounded below by 3 and bounded above by 5. Okay, so what we want to do is we actually want to look at the higher bound here, because we rather be conservative, more conservative than not. So we actually going to say x plus 2 is going to be less than 5. In other words, we're looking at the upper bound in this case. So I can write, thus, if delta is less than or equal to 1 and absolute value of x minus 2 is less than delta, right? X minus 2 is less than delta, then absolute value of x plus 2 times absolute value of x minus 2. Now let's take a look at see how this is going to be, what it is going to be less than. Remember, absolute value of x plus 2, we just showed it's less than 5, right? The upper bound. So this is going to be less than 5, correct? And then absolute value of x minus 2, though, that's going to be less than delta, right? That's given right up here. You see that, our delta inequality? Okay, so that means the product therefore is going to be less than 5 delta. You see how we bounded the side with the epsilon? Okay, so now let me go over here in the blank spot and write this. So what this tells me is that for any positive delta less than or equal to 1 and 5 delta, because remember this 5 delta is replacing our epsilon here, true? Let's see right there, our epsilon. Okay, so it's replacing that. So 5 delta, from here we can write 5 delta must be less than epsilon. Okay, and we have satisfied the condition, because from this divide both sides by 5 and delta will be less than epsilon over 5 there, and we have discovered the value of delta. Okay, so if we want delta again to be less than, remember delta is the distance from 2, how far you are from 2 on the x-axis. It's the value, 2 is the value x approaching. Delta is how far you are from 2, plus or minus. So when delta is less than or equal to 1, then we show that the actual delta would be less than epsilon over 5, and this statement is true. So in the end, we're going to say, because remember we chose delta to be less than or equal 1, and then we found another value for delta. So which one am I going to choose? At this point we say choose delta to be the minimum of either 1 that we picked or your value of epsilon over 5. And when I say your value of epsilon over 5 means anybody's epsilon. So you give me again an epsilon, let's say epsilon 0.1. My delta I give you would be 0.1 divided by 5, which is less than 1. So that would be the delta I'm going to give you. If you give me my epsilon is, let's say, 10. I'm just making that up, which is high. We never go epsilon that high. But to show you how this minimum works, if epsilon is 10, 10 divided by 5 is 2. Well, the minimum of 1 and 2 is 1. So that means your delta should be 1. So if you want to be within 10 units of the limit, which is 2, the answer to limit is 2, within 10 units of that, all you got to do is get within 1 unit of 2 on the number line on the x-axis to meet that requirement. What if I want to be within 1/10 of the limit? Remember, the limit is 2. It's right up here, right? The limit is 2. So if I want to be within 1/10 of 2, let's do 0.1 divided by 5, right? So that's going to be 1/10, so that's 1/50th as a fraction, which means 2.02, right? And that's what delta should be. 0.02 is less than 1. So if you want to be within 0.1 of the actual limit of 2, you should get to within 0.02 unit of x equals 2. That's the value of a. Maybe a poor choice of an exercise because everything has 2 in it in this exercise. The limit is 2, x approaches 2, and that may be causing issue for us also. But anyway, that's how this works. As I said, this epsilon delta is very confusing, and that is why we are appreciative. We thank goodness for and the limit laws. We really don't want to do this going forward. Can you imagine doing this for every problem? It's a nightmare, isn't it? But nevertheless, this is what the definition is. How close do I get in order to satisfy, how close do I get to A in order to satisfy? What are we going to do again? We're going to start with our epsilon tolerance, right? So that means I'm going to write absolute value of f of x minus L less than epsilon. We start with that. Okay. Now, let's simplify this one. X squared plus 2x divided by x minus the limit is going to be less than epsilon. Now, let's do that part on the side. X squared plus 2x divided by x, negative 2x over x. Remember, I need to get LCD here, which gives me x squared plus 2x minus 2x. The 2x is cancelled. This reduces to x squared over x, or simply x. Ooh. So it looks bad, but it's not really as bad as it looks, huh? So this becomes absolute value of x is less than epsilon. And we can write it. Remember algebra here. Our algebraic step is, this is the rewrite of that absolute value. Now let's take a look at our delta tolerance here. Our delta tolerance x minus a is less than delta. But what was a? A is 0, right? A is that number. So absolute value of x minus 0 is less than delta. That means absolute value of x is less than delta, or negative delta less than x less than delta. Look at this one and look at that one. What do you think? So from this, what are we going to get? We're going to equate these. We're going to equate those. And this both cases, one says negative delta equal negative epsilon, the other one says delta equal epsilon, but then multiply both sides by negative and you get exactly the same thing. So choose delta equal epsilon. And again, this was simple. The reason it turned out like this, because the function actually ends up being a linear function, right? Now, there's a little technical. It's like what's going on with a graph. If you graph a linear function, this is the graph of the function, right? But what am I doing? Let me see. This is x. This is f of x equal x, right? This is what the function is. That's what that is. However, the original function was the one that's a rational function, and the domain of this rational function is all numbers except what makes 0 in the denominator, which is 0. So actually we have a hole at 0 in this one. So in other words, if I want to graph this correctly, I have to, here's my hole, there you go. That's what that graph is. But we don't need the graph actually. Okay, so this is number 20. Again, not bad. Maybe we do one more just so you get more comfortable with the proofs. Okay, let's do one like number 21. I think number 22 is pretty easy to do. So we're going to look at one like number 21. Okay, which is the square root of x. So to do one like it, let me make one up. Suppose we want to do this one, something like this. Let me switch my pen again to something that's easier to see. Let me go that way. Okay. This will be our last example, folks. Okay, I know you're getting tired, but Again, it's better to do more than not enough, right? So let's say we want to show that as the limit of x approaching 0 of, we go 4 minus x, square root of 4 minus x. X is 0, square root of 4 is 2. Let's say that's going to be 2. Okay, we want to prove that the limit is 2. Okay, so remember, in order to prove, we need to find the delta in terms of epsilon. And if we are able to find the delta for the epsilon, that means therefore it's got to be 2, because we can make it to 2. Okay. Now let's take a look at this statement. So we have absolute value of f of x, which is square root of 4 minus x, minus the limit. The limit is 2 less than epsilon. Okay, so what are we going to do next? Well, I'm going to rewrite this using our algebraic step. Remember, that's just the rewriting the absolute value statements. So I'm going to write this as negative epsilon less than square root of 4 minus x minus 2 less than epsilon. That's the algebraic step. Get it out of the absolute value. And what are we going to do? We're going to add 2 to all parts, right? So that's 2 minus epsilon less than square root of 4 minus x less than 2 plus epsilon, right? And let's square all parts to get rid of the radical sign. So this is going to be 2 minus epsilon squared less than 4 minus x 2 plus epsilon squared, right? And then what are we going to do? We're going to isolate x, right? So let's subtract 4 from all parts, right? Subtract 4 from all parts, and we're going to get let's see, 2 minus epsilon squared and minus 4 less than negative x, and 2 plus epsilon squared minus 4. Now finally we're going to multiply everything times negative x. I'm sorry, not negative x, but multiply all parts by negative. When we do, we got to change the direction of inequality. But first, here's when everything gets multiplied by negative. They change their signs, right? And the direction of inequality. So this is going to be a negative 4 becomes positive 4 minus parentheses 2 plus epsilon squared. Okay, now let's write it in a form where our inequalities run the usual direction, right? So I'm going to bring this expression here, take that one over there. So it's going to be 4 minus 2 plus epsilon squared less than 4 minus parentheses 2 minus epsilon squared. Wow, look at that. Okay, now this is what our epsilon tolerance comes down to. The delta tolerance is much easier to work with, obviously, because it's a function independent of the function. Okay, so I'm just going to write that delta tolerance now. X minus a less than delta, and remember a is 0. A is the value that x is approaching. In this case it was 0, less than delta. Absolute value of x is less than delta, so x is between negative delta and delta. And there you go, we managed to solve for x. At this point again, we're going to do the same thing. We're going to equate the upper and the lower parts of this, and it's going to look like so. The lower part is 4 minus 2 plus epsilon squared. We're going to set it equal to the lower part of of our delta tolerance. Okay, and then the upper part, let me see, the upper part was delta, right? So it's going to be 4 minus parentheses 2 minus epsilon squared equal to the upper part of the delta tolerance. So lower, lower, upper, upper. And then we're going to solve for delta here, right? So how do we solve for delta? Multiply both sides in the first equation. In this one, multiply both sides by negative. So you get parentheses 2 plus epsilon squared minus 4. That is solved, right? And then the other one already solved for delta. Delta is 4 minus parentheses 2 minus epsilon squared. And now we have 2 to choose from. So what are we going to do? We're going to choose the smaller of the two, right? Choose smaller of parentheses 2 plus epsilon squared minus 4 and 4 minus 2 minus epsilon squared, right? Now we can actually, this is a good answer, but we can actually simplify this further. Okay, let's look at the first part. Okay, let's look at this one. I'm going to expand the binomial. That's 4 plus 4 squared. That's going to be 2 squared. 4 plus 4 epsilon plus epsilon squared minus 4. And then the other one, this one is going to be 4 minus 2 squared is 4, negative 4 epsilon plus epsilon squared. Not that way though, right? Epsilon squared this way. Okay, and then distribute the sign. The 4's actually cross out that way, and then this is going to be 4 epsilon and minus epsilon squared. That's what that ends up being, right? The other one is epsilon squared plus 4 epsilon, right? Now look at these two. Which one is smaller? Think of it this way. This one is 4 epsilon and we're subtracting a positive number from it. Remember, epsilon is positive. The other one, you have 4 epsilon, right? You're adding epsilon squared to it. True? I just swapped the epsilon squared plus 4 epsilon, rewrote it this way. So both of these have 4 epsilon. Here you subtract, here you add. Well, which one is the smaller? That. So I can say leave it like this, or this would imply delta is actually going to be 4 epsilon minus epsilon squared. There you go. That's if you pursue that further. Okay. All right. So we're done with this section. Again, hopefully you have a good grasp of this. Because this is usually a very problematic section for a student. So I hope that I was able to somehow explain this to where hopefully most of you follow it. And again, in terms of future work, we're not going to do this hardly at all. It's just a passing phase, but we do need to know it for our exam, because section 1.3, this is all we're doing. So on that, we are done with this section, and I'll see you in another section. Since we are done with everything we were supposed to do in this section, let's finish off completely. Actually, I just thought about this. Let's prove one of the limit laws. Okay, now the rest of them are done in a very similar manner, but I think it's good enough to see one of these and how it is proved. Okay, so I have actually the addition law of limits. The addition law of limits says that limit of the sum of two functions is equal to sum of individual limits of those functions. Now here our assumption, of course, is that the limit of f of x and limit of g of x are defined, and that's the only assumption we have. Okay, so we're going to begin for this proof. We're going to begin by letting epsilon to be positive. Remember, what we want to do is we want to show that if we get close enough to a, right? Remember, absolute value of x minus a less than delta. Therefore, the limit of the sum actually will be the difference between the sum of the function and sum of the limits is going to be less than epsilon. Okay, so with epsilon positive, let me write down what I just said. Let this be that. So this is what we want to do. We want to find a positive delta such that whenever we are close enough, again, sufficiently close to a within delta, and then the absolute value of f of x plus g of x, that's our sum function now, is going to be that would be absolute value of the sum function minus the limit of the sum is going to be less than epsilon, right? That's what we want to show. So let me actually stop now and give you an inequality which is known as triangle inequality, okay, because that is our next step in the proof. Okay, so what I have here is what we want to actually show, but in our first step, actually very first step, requires the knowledge of this inequality. Note, so this is called triangle inequality, and there are different versions of this triangle inequality. The form that I'm interested in is absolute value of a plus b is less than or equal to the absolute value of a plus absolute value of b. So what does this triangle inequality actually does for us in general is that it will give us an upper estimate for the size of the sum of two numbers in terms of the sizes of the individual numbers. Okay, so for example, let's say a is 7, b is negative 2. Absolute value of 7 plus negative 2 is going to be less than or equal to absolute value of 7 plus absolute value of negative 2. Absolute value of 5 less than or equal to 7 plus 2, 5 less than or equal 9. See how that works? So this is simply called triangle inequality, and there are several versions of this triangle inequality. So again, it gives us an upper estimate for the size of the sum of two numbers. Okay, so our first step actually in the proof is inspired by the triangle inequality. So I'm gonna write the above statement, this statement that you see, this one right in here. Using this triangle inequality, I'm gonna write absolute value of f of x minus L plus parentheses g of x minus m. All I've done here is rearrange the terms of the absolute value. I grouped f of x and L together in here, and then g of x minus m is in here. Okay, that's what I've done. So, having done that, that's going to be less than or equal to, using triangle inequality, absolute value of the individual sums. Okay, that's going to be this part plus absolute value of g of x minus m. So in my triangle inequality, think of it as this. This is a plus b. I'm saying it's less than or equal to absolute value of a plus absolute value of b. That's what that is. Motivated by triangle inequality. Now, having done that, our next step, let me erase this. So my proof is in one piece regarding to what we want to do. Okay, now we were told that the limit of f of x is L, correct? So let's take advantage of that. Since we know that the limit as x approaches a of f of x is L, so what's the implication of that? So that means, therefore, this function must satisfy the epsilon delta definition of a limit, doesn't it? So that means, here's our existence modifier, means there exists a, call it delta 1 for now because this is for the first function. There is a delta, positive delta, such that absolute value of x minus a less than delta 1 implies that absolute value of f of x minus L is going to be less than epsilon, right? Okay, now remember we said that let me say something. If, for example, if 5 is less than 7, right? Therefore, it's going to be also less than. Let's see. Well, let me not do that. You get confused. But actually, let me do this. Sorry about this. I just want to make it easier for you. Okay. So instead of epsilon, why don't I do this? Let me make this epsilon over 2. Okay. Remember, these epsilon is an arbitrary number, like 0.1, 0.05, 0.001. So instead of letting it be epsilon, I want this to be half epsilon. Okay. Now, by same token, we can write the same thing for g of x. If limit of g of x exists, and it's m as x approaches a, therefore there exists a delta for that one also, such that absolute value of x minus a is less than delta 2, and this would now imply that the difference between the function and the limit is going to be less than, call that again, epsilon over 2. Remember, epsilon is a number, so if I say epsilon is 0.4, well, I could have said epsilon over 2 was 0.4. The point is that here I just have a very small number. Okay, so there you go. I can let epsilon over 2 be epsilon. So it's okay. It's legal to do what I'm doing here. Okay. Okay, let me erase this one. Okay, so again, those are based on the fact that we know the limits exist. Now, if we let delta to be the minimum of these two, right? The minimum of delta 1 and delta 2. Okay, that's what we're gonna let it be. Now, here's actually what we want to prove. If absolute value of x minus a is less than delta, then absolute value of x minus a is going to be less than delta 1. Okay, so that absolute value of f of x minus L is less than epsilon over 2, and the absolute value of x minus a is going to be less than delta 2. Okay. And also we can say so that g of x minus L is going to be less than epsilon over 2. So what do we have here as a result? Therefore, absolute value of f of x plus g of x minus L plus m is going to be less than epsilon over 2 plus epsilon over 2's, and this would be equal epsilon, right? So this shows that the limit as x approaches a of f of x plus g of x will equal to L plus m, therefore that must hold. Okay, so there we have it. So this would be the proof. Again, I thought since we've seen the epsilon delta definition of a limit, that you might want to see how one of these proofs is done. Okay, and I know it's hard to follow this, but again, just to recap this one, we're truly done with this. You can prove, by the way, other limit laws this way, but I'm sure probably not many people are interested in this one, right? So the key was that triangle inequality. And let me make sure I did everything right. Okay. So if that is true, I'm just reading this out loud. Let me actually pause and just to make sure everything looks good. Okay, actually I found something I need to add to this. So again, here's where I'm looking at. if absolute value of x minus a is less than data. So in other words, we're going to let x minus a be less than delta. Remember, we define delta to be the minimum of delta 1, delta 2, right? So we know that absolute value of x minus a is less than delta 1. So f of x minus l is less than epsilon over 2, because the reason for that was because the limit of f of x was defined. And then I need to make this, put an AND statement here. And we know that absolute value of x minus a is less than, actually this should be delta 2, because now we're looking at g of x. So that this is true. Again, both of these statements, this one, and then separately this one. Okay, both of these are true by definition of limit of f of x and g of x. So therefore, absolute value of f of x plus g of x minus l plus m has got to be less than epsilon 2 plus epsilon halves plus epsilon halves, which is epsilon. Yeah, that looks good. Okay, I'm okay with it. So we're done. Looks like we managed to do this. Okay, so this is going to wrap up our lecture truly this time. We're done with section 1.3.